Well, let's now turn our attention to a new formulation of geometrical optics, and this video will be an introduction to that new formalism. Uh, Recall that in the paraxial ray approximation, all rays make a very small angles with the optical axis. They're almost parallel, but not quite. And to a certain extent, with the advent of lasers and the laser system, nowadays the optical equipment and instrumentation that entail lasers, in lots of cases anyway, can be called extremely paraxial because the laser beam is for all intents and purposes, the angles that it makes with the optical axis is going to be very, very small. In any event, for such systems, the matrix formulation is a method that is used a lot. Matrix formulation of optics is commonly used, and we'll begin our study of matrix optics with this session. Basically, what we want to do is represent and trace arrays through a system using a matrix, a column matrix for us that entails the height above or below the optical axis and the angle that the ray makes with the optical axis. So for us, y1 is where the ray is at a given position x along the optical axis, and theta 1 is the angle that it's at that same position. Y could be positive or negative. If y is positive, then it's above the axis. If it's above the optical axis, and if it's negative, y is below the axis. That's the same convention that we've used earlier. We likewise look at this entry angle here that it makes. If you have the optical axis parallel to it, so the entry angle at this point at x1 is this angle, and again we measure it, the angle counterclockwise or clockwise from the optical axis, or parallel to the optical axis. So this one has a theta 1 that's positive. Likewise, here we have a theta 1 that's or theta 2 that's negative because it's a clockwise, counterclockwise positive. Clockwise from the optical axis is negative. And of course, it's at a height above the axis. So our variables are that the y variable is the distance from the optical axis at x1 to the point where the ray is at that point along the optical axis, and theta 1 is the angle it makes with the optical axis when it's at the point x1 as well. Similarly, y2 and theta 2 characterizes the ray at this position x2 at a further point down the optical axis. Well, in this formulation, the propagation of light from x1 to x2 can be viewed as the transformation of this pair y1 theta 1 to y2 theta 2. Or in terms of column matrices, we've got a transformation y1 theta 1 transformed by a transformation matrix, linear transformation, y2 theta 2. And in a certain sense, if you know what the form of this matrix is, you don't really have to know what's causing. There could be lots of instruments there. It's an optical system that is more or less like a black box. All we need to know is how it's characterized by this matrix M, and how it transforms an entry matrix at x1 with and maps that into an exit ray on the other end of the optical system. So the optical systems are generally represented by a matrix, which is the transformation matrix that takes the entry y1 theta 1 to the output y2 theta 2. There's different notations for it. Some people use T because it's a transformation matrix. It's usually called the optical system matrix. Lots of people will represent its components. It's a 2 by 2 matrix because we're transforming a two-component column matrix into another two-component column matrix with a square 2 by 2 matrix. The elements of it are A, B, C, and D, sort of traditionally, and so people have gotten into the habit of calling this the ABCD matrix. But in any event, one can represent as really as complex or as simple of an optical system as you would like with a single matrix with these elements A, B, C, and D matrices that characterize the optical instrument or the system. This matrix M is called the optical transfer matrix, and it completely characterizes the optical system in terms of inputs being mapped to outputs. As a result, this matrix, the optical system, can be extremely complicated, but ultimately it's just represented by four numbers: A, B, C, and D. Usually, for complicated optical systems, we try to build them up from simpler optical transformation matrices and applied sequentially, one after another, and we'll see how to do that in the videos that follow this one. Let's get some transfer matrices for a few simple cases. And these are actually very useful. One is simply a propagation of a ray through uniform space, and we just use what we know. If I've got a nice uniform index of refraction here, that an entry ray on this side at x1, it just travels in a straight line, and it will exit over here at x1 plus d. So this horizontal distance from the entry to the exit is the total distance, horizontal distance d. It enters over here at angle theta 1, and since it's a straight line, it exits at the angle theta 2, which is also equal to theta 1. So theta 2 is equal to theta 1 for straight line propagation, which is what we're assuming. And then the relationship between the y2 and y1 can be obtained by looking at this little triangle here. It's a right triangle, and the tangent of theta 1 is this distance, and if you look at that, the total distance is y2. This bottom part is y1, so this side of the right triangle here is y2 minus y1, and so tangent theta 1 is the opposite over the adjacent, so y2 minus y1 over the adjacent side, which is d. And again, small angle approximation. The angle, tangent of an angle is approximately equal to the angle, and we're close to that in these paraxial ray approximations. And I can solve this top equation for y2. It's equal to y1 plus d theta 1. And I just carried it on here. Theta 2, as I said, theta 2 has to be equal to theta 1. So really I have the simplest of transformations, the identity. But I'll write that in terms of 0 times y1 plus 1 times theta 1. And I can write this in matrix form. I get the outgoing array characterized by y2 theta 2, this column matrix. And over here, the entry, y1 theta 1, and the matrix multipliers, well, you can just read that off. The matrix of coefficients is 1d, 0, 1. And so we get the translation matrix, which is just free space propagation over a distance d along the optical axis is characterized by this matrix here. So a pretty simple case. Another simple case is refraction at a planar interface. Let's take a look at a point x1 that's right on the interface between the planar boundary between a material that has index of refraction on this side n1 and on the other side index of refraction n2 over here. And I know from Snell's law that n1 sine theta 1 has got to be equal to n2 times sine theta 2. Again, use the small angle approximation. Sine of the angle is approximately equal to the angle. And then I can solve this for theta 2 as a function of theta 1. If I rewrite these, well, if you look at this, on this side you would probably call it I'm entering at y1 theta 1, and on this side you're exiting at y2 theta 2, but obviously y1 and y2 are the same value. And so I get y1 equals, or y2 is equal to y1, and theta 2 is, as I indicated above, is n1 over 2 theta 1. And again, I can write these out in a little fuller expression. It's 1 times y1 plus 0. There isn't a theta 1 over here. And then on this one, there's no y1, so it's 0 times y1 plus n1 over n2 theta 1. From there, just read off the matrix of coefficients, 1, 0, 0, n1 over n2. And we've got the matrix, the transformation matrix that represents the refraction at a planar interface. Remember, n1 is what's on the entry side, and n2 is the index of refraction, corresponding index of refraction on the exit side. Well, we'll see how to combine things and get some more complicated matrices, transformation matrices in videos that follow.